Okay, let's continue from where we left last time. Okay, so we will work at one loop. And suppose we get the following integral from some Feynman diagram that you are calculating at one loop, which is integral d4k over 2 pi to the 4 1 over k square minus delta plus I epsilon square. Whereas I have repeatedly said, delta will be a function of the external momenta, actually the dot products, okay, these are all Minkowskian, of the masses that appear, okay, and the xi's, the Feynman parameters, or because these could be different, let's put j. Okay, so you do this. Suppose you have to integrate this one. You see that this is divergent in ultraviolet region because you have 4 powers of k in the denominator, k square squared, and 4 powers k in the numerator. Okay, so this will diverge logarithmically if you were to put a cutoff lambda. Okay, let's see how things work out when you are doing dimensional regularization. Okay, so this is UV divergent and we call it logarithmically divergent. Okay, when one says something is logarithmically divergent or quadratically divergent, one is imagining a cutoff, okay? Because if you use dimensional regularization, you are not going to get a logarithmic dependence on the cutoff. We'll see what you get, okay? But it will not be logarithmic. So the moment you say logarithmic or quadratic, these things are, these statements assume that you are working with a cutoff regulator. Okay, so what we'll do is to evaluate this, because this is divergent, it's infinite. We see, no matter what I do to this integral, it remains infinite. Okay, so I do a regularization and go to d equal to 4 minus 2 epsilon. Okay, where epsilon is positive. Okay, so when epsilon goes to 0, you recover this integral. Okay, in that limit. So epsilon is some positive number, so that the number of dimensions are lower than 4, because 4 minus 2 epsilon is something small. Okay, there is no, it is not necessary that you put this 2. Okay, you can work with 4 minus epsilon also. It is just a choice that I have made. Okay, but if you don't like, you don't have to. Okay, so with this, your integral becomes, the modified integral or the regulated integral becomes d4 minus 2 epsilon over 2 pi to the 4 minus 2 epsilon, okay, 1 over k square minus delta plus I epsilon square. Okay, and now this integral is convergent because number of dimensions is less than 4. Okay, okay, so let's evaluate this to see explicit form of the singularity in epsilon going to 0 limit, okay, or d going to 4 limit. So we have evaluated this integral already, okay, and I'm just going to put d equal to 4 minus 2 epsilon in the result. So let's go back and see somewhere here. I should have that result. What happened? Animation timeline. Yes, I can check. This one. Okay. d dk over 2 pi d 1 over k square minus delta plus I epsilon to the n. So capital N here in the present integral that I am evaluating, n is 2, which means you have 2 Feynman propagators in the diagram, and d I have put 4 minus 2 epsilon. So I'll take this result and put d equal to 4 minus 2 epsilon, okay, and capital N equal to 2. That's what I'm doing. Let's okay, I will not copy and paste it there. You can verify that what I am doing is correct. Okay, so in that formula that I showed to you, I'll put d equal to 4 minus 2 epsilon. So I times, it has a minus 1 power capital N. So capital N is 2, this 2, okay, this one. Then you have 4 pi power d, which is 2 minus epsilon, d over 2, which becomes 2 minus epsilon. Okay, then you have gamma of, let me show you again. So in the numerator you have gamma of capital N, which is 2, minus d over 2. D over 2 is 2 minus epsilon. Okay, so 2 minus 2, that cancels and it leaves only epsilon. Okay, because this minus cancels the minus epsilon you get. So that makes it gamma of, I have missed one factor. I want to write that one before that. So this, and then you have no, everything was fine, everything was good. What did I remove? Yeah, gamma of epsilon, and then in the denominator you have gamma of capital N, which is gamma of 2. Okay, and then we have 1 over delta minus I epsilon, and you will see that it's useful to keep this I epsilon. Okay, and this exponent becomes epsilon. Okay, it had the same argument. The power here was the same as the argument of gamma function, and that is why they both are epsilon. Okay, now gamma 2 is 1 factorial, which is 1. So that is what I will put, and this thing I can write as I over 4 pi square. Okay, now I am still left with 4 pi to the minus epsilon. Okay, which goes in the numerator and becomes 4 pi to the epsilon, but I also have this 1 over delta minus I epsilon, so I will include it here. Okay, and then you have gamma of epsilon. All the kinematic dependence is contained in delta. Okay, and this remaining things depend on epsilon only. Okay, so where is the singularity in all of this? When I put epsilon to 0, of course this factor is non-singular. Something to the power 0 is 1, so that's not going to give you any divergence. The singularity is in here, in gamma of epsilon. So we should know then how gamma function behaves near 0. Okay, so how gamma z behaves when z approaches 0, because that's the limit we are interested in, and here is the result. Maybe I should, yeah, here itself. So gamma of epsilon behaves as 1 over epsilon minus Euler gamma. This is again a gamma, it's called Euler gamma, plus terms that are order epsilon. Okay, so you see that it is singular, as you already know, and the behavior is like this. Okay, gamma of epsilon is 1 over epsilon minus Euler gamma, where Euler gamma is a number which is 0.5772. Okay, and of course you have more terms, more digits in this, and then you have terms which are order epsilon. Okay, so you see that this integral at one loop with two propagators, the Feynman diagram having two propagators, okay, it's going to give you a pole, a simple pole, because gamma of epsilon is going to give you 1 over epsilon, so it provides you a simple pole. Okay, so what looks like as a logarithmic divergent thing when you use a cutoff appears as a simple pole when you use dimensional regularization. Okay, so let's put this here. I over 4 pi square, okay, 4 pi over delta minus I epsilon. This epsilon is different, okay, and this epsilon is different. Maybe I should use this epsilon, which is coming from Feynman prescription. I will write as this one, and this one, this dimensional regulator as epsilon, gamma. So what is gamma of epsilon? It's 1 over epsilon minus Euler gamma plus order epsilon. Okay, now I should work with this expression. I will write it again. So did I give a name to this integral? No. So let's call this I. So I is equal to, I have found that it is I over 4 pi square times 4 pi over delta minus I epsilon this I wrote already, 1 over epsilon minus Euler gamma plus order epsilon. Okay, so this is I over 4 pi square times this one. Let's expand in epsilon, okay, in powers of epsilon. So the lowest order term is 1 plus epsilon times log of 4 pi over delta minus I epsilon, okay, and then you have order epsilon square term. Okay, this expansion I can write easily, and then you have 1 over epsilon minus Euler gamma plus order epsilon terms. Okay, now let's carefully look at all the terms. Okay, let's look at first the order. Let's look at first the most singular piece. Okay, you have 1 over epsilon. So the most singular term is generated when you multiply this with the lowest order term in epsilon, which is 1 here. Okay, and there is one way, only one way, so that gives you 1 over epsilon. Now let's look at terms of order epsilon to the 0. Okay, because the next thing in powers of epsilon is epsilon to the 0, meaning a constant. Okay, so how do you generate that? When you multiply this constant here with that constant there, that gives you one such term. So let's write it here, minus gamma e, and the other way you generate it is when you multiply this 1 over epsilon term with the order epsilon term. Okay, so that will give you log 4 pi over delta minus I epsilon. So it gives you log of 4 pi minus log of delta minus I epsilon. So I will write it separately. Okay, and now any other term that you generate. Okay, so this is all order epsilon term, order epsilon to the 0 terms, constant terms. Okay, constant meaning not constant but order epsilon to the 0 terms. So this is what you have got at this rate, and then you whatever is left is order epsilon terms here. Okay, there are many ways in which you can generate order epsilon terms. For example, by multiplying this epsilon log 4 pi with minus gamma I. That will be an order epsilon term. Okay, so that shows you the explicit form of singularity. So as I said, you get a singular simple pole. Okay, in dimensional regularization for the integral that we have looked at. And note that no matter what kinematic factors appear here, okay, in the delta, you are going to get, in addition to this singularity, 1 over epsilon log of 4 pi minus Euler gamma. So that constant is going to appear. Okay, this will be of we'll have to. There will be things which I will be saying later about this constant. So let's keep it in mind that when you are working at one loop, these constants are going to appear in precisely this combination. Okay, and the kinematic dependence is contained in this logarithm of delta. Okay, and also note that you have delta of minus I epsilon. Okay, so it's useful to keep this minus epsilon. I didn't drop it here. Okay, I haven't dropped the I epsilons. I am being careful in keeping it. And now you see why it's useful, because see, the delta could be a negative quantity, right? Because you know that I have, instead of using m square when I was in Euclidean space, I switched to delta. Okay, because delta is not necessarily positive definite. So log of, you could have log of a negative number here, negative quantity here. Okay, depending on the PIs that you have. Okay, and in that case, it's important to know what's the value of log, and that you can know only by knowing whether you are above the cut or below the cut, the branch cut of the log. Okay, and for that you need to know the sign of I epsilon. Okay, you need to know on which side you are of the branch cut, and that is why you need this I epsilon correctly, and then this is whether minus I epsilon or plus I epsilon becomes crucial. And since we have carefully carried all this, I know that it is minus I epsilon, okay, where epsilon is positive, this epsilon. Okay, so one has to be careful with the arguments of log. So you better keep track of the I epsilons. Okay, is there anything else? No. So as far as this integral is concerned, this one, okay, when I use dimensional regularization and go to epsilon going to 0 limit, this is the form of the integral I get. Okay, now let's look at another integral which you will get, and you know that it is divergent with the diagram divergent and has only one propagator. So here I took a Feynman diagram which had two propagators, so that I get to this form. Okay, and we already talked that there is one more integral that will be divergent at one loop, okay, which you get from tadpole. So let me draw that one, or self energy. So second integral, let's look at another integral that is divergent at one loop in 4 dimensions is this one. Here the power is 1. Okay, so only one propagator, and previous one was with 2 propagators. And you know that if you have more than 2 propagators, let's say you have 3 or 4 or whatever, then this integral will be convergent, because if you have 3 here, then 4 powers in the numerator and 6 powers in the denominator, so it's convergent. And that's why I'm interested in looking at only these 2 integrals here. Okay, good. So this is, what kind of diagram is this? This comes from this kind of diagrams. Okay, only one propagator here. So this is a self-energy diagram. So let's look at what kind of singularity this will give. So going back to the integral here, okay, in this I will put capital N equal to 1 and d equal to 4 minus 2 epsilon. Okay, and this time I will not worry about this this factor, okay, because I have already shown you how to work with this. So let me just show you the kind of singularity that you get, which comes from gamma n minus d over 2. Okay, so n minus d over 2. So capital N minus d over 2, that is the gamma function that you get, where capital N is 1, d is equal to 4 minus 2 epsilon. So what do you get? You get n is 1 minus d over 2, which is 2 minus epsilon, which is minus 1, plus epsilon, which is minus of 1 minus epsilon. Okay, so we have gamma of minus 1 plus epsilon. That is what appears in this integral, which will give you a singularity. Okay, now you might already be aware of that the gamma function, though it is analytical, it's analytic everywhere in the complex plane except for the negative integer values and the origin. Okay, so you see when epsilon goes to 0, this goes to gamma of minus 1, which is singular. Okay, and I can easily find out the nature of singularity using the result that I have already given to you. Where was that? This one. Let me okay, let's try to box this one. No, not sure whether it works. Okay, I've forgotten how to do it. Yes. Okay, good. So this is what I'm going to use now. And another very useful result that you should always remember is this. Is this, that z gamma z is gamma 1 plus z, or z plus 1, let's call it this way. Okay, and I will use this now. So I need gamma of minus 1 plus epsilon. Okay, so if I use minus 1 plus epsilon times gamma of minus 1 plus epsilon, then it is gamma of minus 1 plus epsilon plus 1. So that's gamma of epsilon. And this one I know. So from this I can easily determine minus 1, gamma of minus 1 plus epsilon as 1 over minus of minus 1 plus epsilon times gamma of epsilon. Okay, which is simply minus 1 plus epsilon times 1 over epsilon minus Euler gamma plus order epsilon square, order epsilon terms. Now this denominator, okay, it will start with 1 or minus 1, and then it will have order epsilon terms. Okay, so expanding this 1 over minus 1 plus epsilon doesn't change the order of the pole. Okay, so it gives, because it starts with 1, and when you multiply with 1 over epsilon, it gives you 1 over epsilon. So you see again that this integral also is giving you simple poles. But if you had used a cutoff regulator, you will not get a logarithmic divergence, right? Because this is not log divergent. But when you are using these dimensional regulator, you are still getting a simple pole. Okay, so singularity appears here also as a simple pole. Okay, and this is because we are working in 4 dimensions and at one loop. If you were to go to higher loops, then this will change. Okay, these will not be simple poles. Okay, and as I said, if n is greater than 2, capital N is greater than 2, more number of denominators, then the integral is converged. So I have then exhausted all the divergent integrals that are going to appear at one loop in 4 dimensions. Okay, so I have completely exhausted that set, and now I will start looking at dimensional regularization and how to proceed with that. Okay, and I think I should do it in the next video, not in this one. Okay, fine. So let's meet in the next video then.